Hello students, welcome to EPG Pathshala. I am Tanushree Shahadas Gupta, Professor and Associate Dean in S.N. Bose National Center for Basic Sciences in Kolkata. I belong to the Department of Condensed Matter Physics and Material Science. I am also the coordinator of the Thematic Unit of Excellence on Computational Material Science set up within S.N. Bose Center. In this lecture, we'll focus on the basis sets. To solve the single particle or the single electron Kohn-Sham equations discussed in previous lecture and to obtain the eigenvalues, that's the band structure and the eigenfunctions, one has to choose an appropriate basis set to expand the Kohn-Sham wave functions. The basis set depends on the specification of a given problem, such as the crystal symmetry, the nature of the involved elements of the periodic table. Computer codes based on several different basis sets have been developed in the last few decades and are widely used for electronic structure calculation of solids, clusters, and molecules. One electronic structure code differs from another essentially in the choice of the basis set. We'll discuss two very popular basis sets, namely the plane wave basis set and the Gaussian basis set. Depending on the choice of the basis functions, the codes or the methods can be broadly classified into two categories, such as those based on the delocalized nature of the wave functions and those based on the localized nature of the wave functions. For example, the plane wave basis set is an example of the former, and that of the latter is the Gaussian basis set. It's worth mentioning that John Pople shared the Nobel Prize with Walter Kohn in 1998, as we mentioned in the previous lecture, for his development of the computational code that used the Gaussian basis set. In a typical plane wave calculation, a finite number of plane wave functions are used below a specific cutoff energy, which is chosen for a certain calculation. These basis sets are popular in calculation involving periodic boundary conditions. Certain integrals and operations are much easier to code and carry out with plane wave basis function than with their localized counterpart. In practice, plane wave basis sets are used in combination with an effective potential called the pseudopotential, so that the plane waves are only used to describe the valence charge density. This is because the core electrons tend to be concentrated very close to the atomic nuclei, resulting in large wave function and density gradients near the nuclei, which are not easy to capture by a plane wave basis set unless a very high energy cutoff and therefore small wavelength is used. We'll discuss state-of-art pseudopotentials implemented in the modern day codes like the VAS or PWSCF, which these days is known as quantum espresso. In addition to the localized basis sets like plane wave, Gaussian basis set is also widely used in quantum mechanical calculations. In linear combination of atomic orbitals approach, the atomic orbitals are well described with Slater-type orbitals, as Slater-type orbitals decay exponentially with distance from the nuclei, accurately describing the long-range overlap between the atoms and reach a maximum at zero, well describing the charge and spin at the nucleus. The Slater type orbitals are computationally difficult, and it was later realized by Frank Boyce that these Slater type orbitals could in turn be approximated as linear combinations of Gaussian orbitals instead. Because it is easier to calculate overlap and other integrals with Gaussian basis function, this led to the huge computational saving, which was made popular by John Pople. With this brief introduction, we now move on to the details of the formulations of plane wave and the Gaussian basis set. The objectives of this lecture are as listed in the following. First of all, there are various different DFT-based first principle methods which differ in choice of basis functions. We shall discuss two important basis sets, namely plane wave and Gaussian. In the context of plane wave basis set, we'll discuss the concept of pseudopotential, which is an essential concept for implementation of plane wave basis. We shall discuss a few modern pseudopotentials which are used in the codes that are used in recent time. We will discuss the Gaussian basis set, we will discuss its advantages and practicality of use of Gaussian basis set. To solve the single particle Kohn-Sham equation, which was discussed in previous lecture, and to obtain the eigenvalues, which often gives rise to the band structure, and the eigenfunctions, one has to choose an appropriate basis set to expand the Kohn-Sham wave function as shown below, which is given by this psi I equal to summation over alpha C alpha phi alpha, where psi is the Kohn-Sham wave function and phi alpha is the basis set with this coefficient C alpha. The basis set depends on the specification of a given problem, such as the crystal symmetry, the nature of the involved elements of the periodic table. Computer codes based on several different basis sets have been developed in last few decades and are widely used for electronic structure calculation of solids, clusters, and molecules. Depending on the choice of basis set, these codes or the methods can be broadly classified into two categories, such as those based on delocalized nature of the wave function, as I mentioned in the introduction, and those based on localized nature. We shall discuss as an example of the former the plane wave basis set and the Gaussian basis set as the example of the latter. Many fast principle methods based on density functional theory adopt plane waves as the basis functions to solve the Kohn-Sham equation. The reason for the high demand of the plane wave basis are the following. Firstly, the basis set is independent of atom position and species. Secondly, forces acting on atoms are equal to Hellman-Feynman forces, thus no basis set correction to the forces is needed. Thirdly, and most importantly, it takes advantages for the efficient algorithms like first Fourier transformation. One major problem, though, in use of the plane wave basis set is a large number of plane waves is required to describe the wave function close to the nucleus, which is defined as the core region. This is primarily due to two reasons. Firstly, electrons are tightly bound to the nucleus in this region, that's the core region. Wave function in this region are rapidly oscillating due to the orthonormality requirement with a valence electron wave function. One way to circumvent this problem is to replace the strong Coulomb potential of the nucleus and the effects of tightly bound core electrons by an effective ionic potential acting only on the valence electron, known as the pseudopotential. In the following, we'll elaborate on this concept of pseudopotential. So, the plane wave expansion has to accommodate two radically different features of the block function due to the form of the lattice potential, which is shown in this figure. Inside the atomic core region, the potential is practically spherically symmetric and it's deep. And the wave function psi in this region has rapid oscillations and angular dependence of an atomic wave function as is shown here. In the region between the ion cores, the potential is nearly flat and reflects the translational periodicity of the lattice. Accordingly, the wave function psi is slowly varying in the manner of plane waves joining smoothly from one cell to another by virtue of Bloch's theorem. Considering the example of metal like aluminium, the plane wave part of the Bloch function is about 7/8 of the total volume. For the remaining 1/8 of the total volume, a lot of plane waves are needed in order to represent the atomic-like oscillation of this psi k. For this region, of plane wave expansion will actually need a lot of terms to converge. The orthogonalized plane wave concept or the method given by Hering provides a way of handling with poor convergence of this plane wave expansion arising from these atomic-like oscillations. With this, we now start with discussing the orthogonalized plane waves. Orthogonalized plane waves are literally plane waves that have been made orthogonal to the occupied ion core orbitals. Consider a set of Bloch functions constructed out of the core state as is shown here, which is given by Btk, where k is the wave number, which is given by summation over L e to the power I k dot L times Btr minus L, where L basically describes each of the positions of the ions. A core orbital, such as given by Bt, is strongly localized so that there is no more than a combination of a degenerate one-electron states, each corresponding to the localization of the electron on a particular atom. This is actually a solution of Schrödinger equation of the whole crystal corresponding to one of the core levels having an energy given by epsilon t. It could form, therefore, a narrow band which is fully occupied. The higher states, being solutions of the same Schrödinger equation, must be orthogonal to Bt, so that we should have this expression that the product of psi k and Btk is equal to 0. Since psi k must look like a free electron wave function in the interstitial region, let us try the following function chi k, which is equal to e to the power ik dot r minus a summation over t with a coefficient beta t times btk. This coefficient beta t must be of this form given here, so that to satisfy the orthogonality condition which is just mentioned here. This is a good guess for higher state because it works like e to the power ik dot r, the plane wave, in the interstitial region where each btk is small because the core states are highly localized. And yet within the core itself, it will be orthogonal to all the core states. We use these OPWs as is shown here as basis set for our wave function as the solution for Schrödinger equation. So we have this psi k given by summation over capital K, where capital K is the reciprocal lattice vector alpha times chi. We use the variational principle to minimize the energy and determine the coefficients alpha. The procedure converges with surprising rapidity in some of the cases. A single OPW is often quite sufficient to represent the wave function over large regions of K-space. 3 to 4 terms may give rise to quite a good picture even in every corners of a Brillouin zone. Now the question is, why is that? Supposing that psi k is the exact wave function with some definite values of this coefficient alpha, and considering the function phi, which is given by summation over capital K alpha times e to the power I k minus capital K dot r, we can write psi equal to phi minus summation over t product of bt and phi times bt, forgetting this k index at the moment. Putting this into the Schrödinger equation given by capital H psi equal to E psi, and using that H bt is equal to epsilon t bt, which is the eigenvalue corresponding to bt, one gets this following expression, which is shown here. One thus has, just from this equation, taking this psi epsilon times phi into the left hand side, which is given here, shown here with this small readjustment. So this above equation, which was shown in the previous slide, may be looked as a new Schrödinger equation for a smoothened wave function phi, which satisfies a new equation of which the Hamiltonian is given by h plus Vr equal to minus h car square 2m delta square plus u, where u is the original crystal potential, plus Vr, where Vr times phi is summation over t epsilon minus epsilon t times bt phi. This is just as if we have to find the plane wave solution for the eigenfunctions in a pseudopotential, which is given by gamma equal to u plus Vr. U being an attractive potential of an atom is negative, especially near the origin where r is equal to 0, while Vr, as is shown here, containing epsilon minus epsilon t and square of the core orbitals is a positive term. Therefore, there is some cancellation between them, reducing the value of this effective potential gamma as is shown in this figure as V pseudo. This function phi may be called as a pseudo wave function in which satisfies an Schrödinger equation of having an effective potential which is relatively weak. With this, we are back again at a relatively simple, nearly free electron model. Physically, the cancellation may be viewed as the manifestation of the Pauli exclusion principle, which in this context requires the valence wave functions to be orthogonal to the occupied atomic core orbitals. This is manifested through rapid oscillations of the true wave function in the core region, as is shown in the figure, where the potential is deep and attractive. Such rapid oscillations give rise to high kinetic energy, which act as a repulsive potential in the ion core region. The valence electron thus sees only a weak potential, which is shown here, named as pseudopotential. The effective electronic wave function, which is also shown here with a solid line, does not have all this rapid oscillation which was present in the true wave function. Let us now discuss the form of this pseudopotential a little more. The pseudopotential VR stands for a non-localized operator, which is given by this form, this. And the VR acting on phi is therefore given by VRR prime times phi R prime integrated over R prime. This VR part of the pseudopotential makes the entire thing a non-local potential. The cancellation described in the earlier slide, although never complete, it cannot be made completely complete, can be improved by suitable choice of the core functions. Indeed, the whole process of constructing VR is not unique. One can show that the valence eigenfunctions of the Hamiltonian H plus VR are the same for any operator of this form where VR phi is equal to summation over T Ft times phi times Bt, where Ft are completely arbitrary function. For example, if one chooses Ft as equal to minus u times Bt, then gamma phi, where gamma is the pseudopotential, is equal to u phi minus summation over T b times u phi times Bt, which would be a perfectly valid solution. Thus, we may subtract from V any part that can be expanded as a sum of core functions. The operator VR, remember, always projects phi onto the manifold of core states. But the valence eigenfunction that we are seeking is orthogonal to this manifold, so that the addition to the operator VR to the Hamiltonian makes no difference to the eigenvalue problem in the space of valence eigenfunctions. There are two principal criteria to judge the goodness of a pseudopotential. One is the transferability. A pseudopotential is transferable if it works reasonably well in different environments. And another is the softness. A pseudopotential is soft if it requires less number of plane waves. To make these two criteria fulfilled, several methods have been developed. There are two kinds of pseudopotential that are widely used, namely the norm-conserving pseudopotential and the ultra-soft pseudopotential. Let us first discuss the norm-conserving pseudopotential. Norm-conserving pseudopotentials are constructed with an extra constraint that the pseudopotential or the wave function must ensure that the charge within some core radius, let's say RC, is the same for the pseudo, which we show here as phi ps, and the all electron shown as AE wave function, that is integral of this modulus of phi AE square integrated over the space should be same as phi ps modulus square integrated over the space. Norm-conserving pseudopotentials work well for most elements except for some first period 2p and 3d elements. In these cases, the pseudo and all electron wave functions are almost identical. With the requirement of norm conservation, it is not possible to make a pseudopotential dramatically soft, and this leads to the concept of ultra-soft pseudopotential. A completely new idea of removing norm-conserving requirement was introduced by Vanderbilt. The motivation was to introduce soft pseudopotentials, and Vanderbilt's ultra-soft pseudopotential can reduce significantly the number of plane waves to express the pseudo-wave functions at the expense of much more complex formulation of the algorithm. Relaxation of the norm conservation condition makes possible to form each smooth pseudo-wave functions independently with the constraint of matching the wave function with the all-electron wave function at this cutoff radius RC. Therefore, one can choose a much larger RC value than for a norm-conserving pseudopotential, where the desired accuracy is taken care of by adding additional auxiliary functions and overlap orbitals. Vanderbilt's pseudopotentials, this ultra-soft pseudopotential, are implemented in number of modern-day density functional theory computer codes such as VAS, PWSCF, which these days goes with the name as quantum espresso. Let us now move on to the discussion of Gaussian basis. In order to discuss Gaussian basis, let us start from the concept of linear combination of atomic orbital basis, which goes with the name as LCAO. One can take the concept in LCAO one step further by considering the following. Firstly, use a number of atomic orbitals. For example, a hydrogen atom can have more than one s atomic orbital and some p and d atomic orbitals. This would lead to a more flexible representation of the molecular orbitals and thus more accurate calculated properties according to the variation principle. Secondly, use of atomic orbitals of certain mathematical form that simplifies the computations but not necessarily are equal to the exact atomic orbitals of the isolated atoms. Functions that resemble hydrogen atomic orbitals are the Slater type orbitals, which we show here as with the expression S nu function of r, are very suitable for expanding molecular orbitals because they have the correct shape given by having a cusp-like behavior near the nucleus and decaying as e to the power minus ar far from the nucleus. We'll see this in the schematic plot in the next slide. However, Gaussian function shown as g nu r are preferred in practice because of their efficiency in computation of molecular integrals having simpler formula. The form of the Slater type orbitals and Gaussian functions are the mathematical forms are shown here. This plot shows the schematic diagram of the Slater type one and the Gaussian one. The huge computer saving in calculating the overlap and other integrals with Gaussian type basis functions has made this method immensely popular, especially among the researchers involved in computational chemistry and computational quantum chemical calculation. In modern code, there are hundreds of basis sets composed of Gaussian type orbitals. The smallest of these are called minimal basis sets, and they are typically composed of the minimal number of basis functions required to represent all of the electrons on each of the atom. In the jargon of quantum chemistry, a single Gaussian function is called a primitive Gaussian type orbital, which can be expressed either in Cartesian or spherical coordinate. In practice, fixed linear combination of primitive Gaussian type orbitals are used, which are called as contracted Gaussians. The simplest kind of contracted Gaussians are known as like STO-NG basis sets. There, the n value represents the number of Gaussian primitive functions comprising a single basis function. Commonly used minimal basis sets of this type are given like STO-3G, STO-4G, or STO-6G like this. The STO-NG basis sets are rather unsatisfactory as they include only one contracted Gaussian per atomic orbital. Improved basis sets can be obtained by including more than one contracted Gaussian per atomic orbital, for example, like double zeta, triple zeta, or quadruple zeta. One contracted Gaussian per core atomic orbital and more than one for the valence atomic orbital. For example, like SV3-21G, 4-31G, 6-31G, 6-311G. If you are a user of the Gaussian basis set, you will come across all these jargons quite often. The improvement in Gaussian basis set can be obtained by introducing two very popular ideas, namely the introduction of polarization function and diffuse function. Let us first discuss the polarization function. It is a very popular common addition to minimal basis sets. These functions are auxiliary functions with one additional node. This gives additional flexibility within the basis set. For example, the only basis function located on a hydrogen atom in a minimal basis set would be a function approximating the 1s atomic orbital. Addition of polarization function effectively allows molecular orbitals involving the hydrogen atoms to be more asymmetric about the hydrogen nucleus. Addition of polarization function in the basis is usually denoted by an asterisk, that's the star, and two asterisks denote the polarization functions are also added to light atoms like hydrogen and helium. Another common addition to the basis set is the addition of diffuse functions. These functions are very shallow Gaussian basis functions which more accurately represent the tail portion of the atomic orbitals that are distant from the atomic nuclei. These additional basis functions can be important while considering anions and other large soft molecular systems. Diffuse function is usually denoted by plus sign and often by this notation aug, which is an abbreviation from the word augmented. As in the case of the polarization, two plus signs indicate that diffuse functions are also added to the light atoms like hydrogen and helium. We emphasize finally that these additional basis sets of these diffuse functions can be important when considering anions and other large soft molecular systems. To summarize, we discussed the two commonly used basis sets in solving the density functional theory equations, namely the plane wave and Gaussian basis sets. We discussed the concept of pseudopotential, which makes application of plane wave basis a viable solution. Different pseudopotentials used in modern density functional theory code has been mentioned. We also discussed the Gaussian basis sets and its different implementation.